Hi, this is the Session 6 assignment. A cognitive agent built from 4 typed layers: perception, memory, decision, and action. The whole thing is handwritten in about 1,000 lines of Python across 6 files. No LangChain, no LangGraph, no agentic framework. Every boundary between layers is a Pydantic-validated handoff. The agent answers research queries by looping over those layers until it produces a typed final answer or hits an iteration cap. Here's the loop. Perception runs once at the start. It reads the user's query, classifies it as one of 5 types: fact lookup, comparison, memory write, memory recall, or synthesis, and picks the Pydantic model the final answer must conform to. Memory loads from a JSO file on disk. Then we enter the main loop, where decision picks exactly one of 3 actions every iteration: call_tool to fetch fresh information, write_memory to persist a durable fact, or final_answer to exit the loop. Action executes that choice, calling MCP tools over stdio for tool use, or writing to the memory file, and returns a typed result. The loop continues until final_answer fires or the iteration cap is hit. 6 source files, every boundary typed. Decision is a discriminated union, so the LLM is forced at the JSO schema level to emit exactly one of the 3 branches. There's no regex anywhere on LLM output. Let's run the first query. Fact lookup: what's the latest stable FastAPI release and the minimum Python version it requires? Cap of 4 iterations. Perception classifies this as fetch_URL. Iteration 2, it has the version 0.136.1 and the minimum Python 3.10, both grounded verbatim in the fetched page text. It emits final_answer. 2 iterations, well within the cap of 4. Worth pointing out, the min_Python field 3.10 lives in the metadata sidebar of the PyPI page, far past where a naive page excerpt would land. Earlier in development, I had the scratchpad capped at 800 characters, and the agent hallucinated 3.8 from training data priors because it never actually saw the requires Python line. Bumping the cap to 6,000 fixed that. There's a longer reflection on this in the README. Next, comparison. Polars versus pandas, which one shipped a more recent breaking change, and what was it? Cap of 8 iterations. This is the open-ended one. The agent alternates web search calls for polars and pandas, then drills into release notes on the pandas side. Notice that on iteration 7, the reasoning explicitly says, quote, "Scratchpad contains sufficient grounded data, pandas 3.0.0 released 21st January 2026, polars 1.0 released 1st July 2024. That phrase, sufficient grounded data, is the agent self-checking against an explicit commit rule the decision prompt now includes. On the first version of this code, the agent drifted past the cap of 8 because it had no awareness of its iteration budget. Adding iteration and max_itis to agent state, and rendering them in the decision prompt with a commit rule, made the loop self-budgeting. The cap was honored this time. What changed was why the agent stopped. Final answer, winner is pandas. Breaking change dated 21st January 2026, the dedicated string type and the copy-on-write default. Both citations are real pandas documentation pages. Now the most architecturally interesting query, durable memory. We are going to run to separate Python processes. The first one tells the agent to remember the user's project stack. The second one asks for a recommendation based on that stack, in a brand new process with no shared state except the memory file on disk. Perception flags this as memory write, and the decision heuristic kicks in. Quote, for memory_write queries, your very first iteration must be write_memory. So iteration 1 writes the user_project_stack record with all 3 components. Iteration 2 emits the memory write tag. 2 iterations optimal. And here's the fact on disk in state/memory.jso, Python 3.11, Pydantic-V3 FastAPI 0.115. The process exits here. State is gone from RAM. Now watch the first line of the second run. Memory loaded 1 fact. Brand new Python process, but the fact written by the previous process is back in memory. That right there is the durable memory checkpoint the assignment is testing. Perception flips memory_relevant to true and weaves the stored stack into the intent line. Quote, compatible with the stored project stack, FastAPI 0.115, Pydantic-V3 Python 3.11. So the stored fact informed perception, not just decision. The agent recommends HTTPX, which is the canonical async client for FastAPI projects. 2 iterations, well inside the cap of 6. Full disclosure on this one, the citation URL is the HTTPX homepage rather than a specific compatibility page, and the version string isn't actually grounded in the scratchpad. That's a real limitation, and there's an honest reflection on it in the README. The genuine fix would be to programmatically validate each field's substring against the scratchpad, not to add more wording to the prompt. The durable memory checkpoint, which is the actual point of this query, did work. Last one, synthesis. Find one CVE in the cryptography PyPI package from 2024 or 2025 and summarize the affected versions and fix. Cap of 6 iterations. Iteration 1, web search for cryptography CVEs. Iteration 2, and this is the key step, the agent doesn't commit from the search snippet. It picks CVE 2024-26130 out of the results and fetches the canonical NVD advisory page. That's the cite and prove heuristic in the decision prompt firing, when the user asks the agent to summarize something that requires a primary source, not a snippet. Iteration 3, final_answer, grounded in the NVD page. CVE 2024-26130. Affected versions 3.8.0.0 through 4.2.0.3, fixed in 4.2.0.4. It's a null pointer dereference in the PKCS12 serialize function triggered by mismatched public-private keys with HMAC hash encryption. All 5 fields sourced from NVD. 3 iterations, well under the cap. Here's the iteration table. 5 queries, all converged within bounds. A in 2 of 4, B in 7 of 8, both C runs into each, D in 3 of 6. 3 architectural takeaways worth flagging. 1. Agents can only ground answers in what their next prompt can actually see, so scratchpad sizing matters more than it looks. 2. Decision layers without iteration awareness will drift. Making the budget visible to the LLM with explicit commit rules is what turned query B from a runaway loop into a self-budgeted one. 3. Prompt-based grounding has a ceiling, and beyond it the real fix is programmatic post-validation of every final_answer field against the scratchpad. 4. Cognitive layers. 6. Source files. No agentic framework. Thanks for watching.